Hey everyone, and welcome back. Today, we're jumping straight into some pretty mind-blowing breakthroughs in both AI and quantum computing that are completely reshaping the future. And these aren't just small tweaks. These are massive leaps forward. So let's get right into it.
It really all begins with one simple but honestly pretty profound question. How does the future of technology actually get built? Where does it come from?
Well, the answer is you build it by tackling the challenges that seem completely impossible right now. Every single innovation we're about to look at is a brilliant solution to a huge problem that has had scientists scratching their heads for years. Okay, so our first impossible problem takes us deep into the weird world of quantum computing. You know, the biggest hurdle, the thing holding it back? Quantum computers are just incredibly fragile. I mean, their calculations can be thrown off by the tiniest little disturbance, a problem they call quantum error, or just noise. And this is a huge deal. We're seeing a major breakthrough from China's Zhutrong Z 3.2 processor in something called quantum error correction. What they've done is use an all-microwave approach. And what's so cool about that is they're not just cutting down on errors, they're doing it with fewer wires, which is a massive, massive step towards actually building a quantum computer that can scale up and solve real-world problems. And this really shows you we are in the middle of a global race to crack this thing. On one side, you have China's 107-qubit processor going all in on that slick, streamlined microwave design. And on the other, you've got Google's 72-qubit Willow, which uses totally custom hardware and different methods. Both are pushing the absolute limits, trying to finally tame that chaotic quantum world. Now, you know, taming chaos isn't just a quantum problem. Let's switch gears and talk about AI, because the challenges there are different, but they're just as big. The name of the game here is making these incredibly powerful AI models way more efficient and, just as important, accessible to everyone. So the key thing to get here is the difference in how AI sees the world. You've got the traditional models on the left. Think of them like someone spelling out a word, letter by letter. Yeah, it works, but man, it is slow and it eats up a ton of computing power. But then on the right, you have this new architecture called VL-JPA, and it thinks in concepts. It's leaner, it's faster, and it's built for understanding things in real time. So what exactly is VL-JPA? Well, instead of generating words one by one, it predicts these abstract representations of meaning, these things called embeddings. You know, it's kind of like how our brains work, right? We don't process things word by word. We process ideas. And this approach is just incredibly efficient. We're talking 50% fewer parameters to train, which makes it lightning fast for things like classifying images or finding information. Now, the other side of this whole efficiency thing is just making it accessible. Normally, the really powerful AI is stuck up in the cloud, right? You need a good internet connection. Well, that's changing. Say hello to Function Gemma. This model is a total game changer because it is small enough to run directly on your phone, on your laptop. And why is that such a big deal? Well, for starters, privacy. Your data never leaves your device. It's also super fast because there's no network lag, and it works completely offline. It can even take a simple command you give it, like set a timer for the pizza, and translate that into the complex code it needs to actually make it happen. That is some serious automation right in your pocket. Okay, so we've made AI leaner, but what happens when we want to go in the other direction? What if we want to make it way, way bigger? Well, as it turns out, as these AI models grow, they hit some pretty hard limits and risk literally breaking while they're being trained. So now let's look at two breakthroughs that are just smashing through those limits. This slide tells a really quick but super important story. See, it started with things like ResNet, which brought in these skip connections. You can think of them as information highways that let signals jump over layers to build deeper networks. Then people tried hyperconnections, which was like trying to build a superhighway system for maximum info flow. The problem? It completely backfired. It caused something called a signal explosion that made the models totally unstable and impossible to train. And that's where the solution comes in, a new architecture called MHC. I absolutely love the analogy here. DeepSeek's MHC architecture basically acts like a safety valve. Instead of just letting the signal run wild and amplify itself until the whole system crashes, MHC puts some constraints on it. It guides it and keeps everything stable.
It's such an elegant fix, and it's a huge deal because it lets us train these massive AI models without them just falling apart. Now, for the second big scaling problem. So, traditional models have a pretty limited memory, or what's called a context window. I'm sure you've experienced this. You give it a long document, and by the end, it's totally forgotten what was said at the beginning. Well, recursive language models, or RLMs, they solve this with this brilliant divide and conquer strategy, which gives them a basically infinite context window. And this is how they pull it off. Think of it like a project manager. You've got this main root LLM that takes a huge task, like, say, summarizing an entire book. It breaks it down into smaller pieces, maybe chapters, and then it delegates each chapter to a smaller, more specialized sub-LLM. By breaking the problem down again and again, it can handle tasks of almost any size without losing track of what's going on. It's brilliant. So let's just take a step back for a second. We've looked at quantum stability, AI getting way more efficient, and AI becoming massively scalable. What happens when you put all of these pieces together? What kind of picture does that paint for the future of computing? Well, a really clear pattern starts to emerge. We are systematically solving the fundamental roadblocks in computing. We're going from unstable to stable. We're shifting from bloated to efficient with AI that can live on your phone. And we are blowing past the old limits to achieve just incredible scale. And all of that leaves us with one final and kind of electrifying question. With these foundational problems getting solved, the training wheels are really coming off. So what impossible problems that we're facing today in medicine, in science, in creativity, things like curing diseases or discovering new materials, what are we now on the cusp of solving tomorrow?